This is Rooms, a procedural generative synthesizer, an immersive reactive audiovisual environment. This is our EET411 senior project presented by Brian Fahey and Joseph Schwartz, advised by Professor Gordon Snyder at ECPI University.
Rooms makes hidden room behavior audible and visible. It treats the live environment itself as the control surface. This isn't just a monitor, and it isn't just a synthesizer on its own. It's a responsive environment that translates spatial and climate data into audiovisual behavior. 4 pillars: real-time sensing, procedural synthesis, a radar scanning HMI, and state-based interaction. The inputs are spatial, distance, temperature, humidity, and user state.
What the customer interviews push forward is accessible hardware using affordable, available parts that can be replaced or upgraded, reliable operation that prioritizes stable sensing, clear feedback, and simple physical controls, and creative use cases aiming for schools, art installations, large public spaces, and exploratory demos.
Our operating principle is a 3-layer system that keeps sensing, visualization, and sound independently tunable. Layer 1 is the sensing layer. The Arduino Mega captures ultrasonic DHT and potentiometer and button states. Layer 2 is the interface. Processing parses the serial packets and renders the radar telemetry. And layer 3 is the synthesis layer. Super Collider receives OS messages and shapes the stereo engine. Data flows from sensors and user input into structured serial packets into OS messages and out as audio.
Environmental values become musical parameters through explicit mappings. Distance from the HCSR04 maps to pitch and filter offset. Potentiometer and button states set mode, waveform, and state. Temperature from the DHT sensor drives drone frequency. Humidity drives filter color. The mapping equation on this slide is the key calculation. It's not decorative, it's the actual translation layer between the room and the instrument. Our prototype is built from ordinary modules assembled into an instrumented room interface. The Arduino Mega is the embedded controller at the center. The HCSR04 mounted on a servo performs the spatial scan. A DHT sensor handles climate input, and an LCD with buttons gives us a local interface. The schematic and hardware details come from our week 3 report and fritzing schematic.
The final build is now layered acrylic and PLA or PETG. It's a housed instrument with exposed serviceable electronics. You can see the breadboard control here in the third picture and the open frame design. Layered assembly keeps the prototype visible, stable, and easy to assemble and service. The sensor head mounted to the servo for scanning is up top. That's mounted on top of the upper acrylic and control panel where the LCD buttons, potentiometers are all housed. Breadboard wiring layer is underneath, and it is a solderless prototyping layer for fast changes. And the acrylic base on the bottom is what the Arduino Mega is mounted to, as well as the bottom breadboard.
For our software architecture, 3 elements handle the real-time workflow. Arduino IDE handles sensor reading, motor control, and serial data packaging. Processing IDE displays the radar scanner HMI, smooths the data, and translates it into OCS messages. The Super Collider generates the real-time audio by mapping that data to oscillators and filters.
For our calculations, current draw is estimated at 1.25 amps under maximum load. We applied a 1.5 times safety factor, giving a requirement of 1.875 amps. That puts our recommended power supply at a minimum of 5 volts, 2 amps. Total power budget comes out to approximately 9.38 watts, so we sized for 10 to 15 watt practical supply. And for ultrasonic sensing, distance is calculated by timing the return trip of the ultrasonic pulse. For our control surface, system behavior is driven by both user input and environmental data. Pitch and filter are controlled by the potentiometer plus distance measurements. The user selects the waveform directly through the button state, and performance buttons handle arpeggiator, freeze, and filter enable. Temperature and humidity continuously influence drone behavior and synthesis parameters in the background.
For our trade study, we compared three options: Arduino plus PC, microcontroller only, and laptop software only. We scored each against audio quality, debuggability, sensor fit, and presentation value. The Arduino plus PC stack won out. It gives us Super Collider's high-quality audio, the Arduino sensor integration, and processing visuals, which was the best balance for a prototype exhibition. Our objective through the trade study summary was to translate stakeholder expectations into system requirements and design selections for rooms, identifying customer needs based on a level of priority, making trade decisions accordingly based on the customer needs, and then implementing those into our design. This is our design failure mode and effects analysis table. We walked through every major component: the servo, the DHT11, HC-SR04, the Arduino Mega, and serial communication, and identified how each could fail, what the effect would be, and how severe it would be on a scale of 1 to 10. The Arduino Mega scored highest severity since a freeze or crash there stops the entire system function. For each failure mode, we also defined a prevention control like watchdog timers, shielded wiring, and calibration schedule.
Our highest risk sits at real-time communication and sensor stability. Serial packet loss from stale or malformed values is mitigated with parse guards and long-duration testing. Servo jitter from an unstable distance scan is checked with sweep timing checks and isolated power. Slow climate response from DHT latency is handled with 2-second polling and smoothed mapping. And OS mismatches where the audio engine misses a state are covered by a message size fallback logic. Here is our physical build. This shows sort of a order of operations procedural for getting the synth running, and we will go ahead and embed a video or share that after the presentation.
Testing confirmed strong integrated performance. One sensor test was conditionally passed. Startup and power, no resets, overheating, wiring faults, or abnormal behavior. A 40-minute continuous servo sweep operation showed no jitter, binding, or enclosure contacts, 6-button controls and LCD, full integration of the Arduino processing Super Collider loop remained responsive throughout. The conditional pass, the ultrasonic distance measured about 4 to 6 centimeters off in a crowded room with the servo sweeping. That means for us, the distance sensor still performs its intended role as a modulation input, but the prototype should not be presented as a precision distance meter without a controlled fixed angle retest. This is our integration evidence, proof that full sensing to sound loop already works end to end. The prototype already demonstrates the complete sensing to sound loop. The Arduino translates a 16 value packet covering mode, controls distance, climate, and state. Processing sends smooth control values over OSC to radar synth. The Super Collider maps that into frequency, cutoff, waveform, LFO, arpeggiator, and filter state. Locally, the LCD and main HMI interface expose live system status as feedback.
In conclusion, rooms reframes environmental data as an interactive media. It's a responsive prototype built on a modular architecture doing live sonification, and we see it as an expandable research platform going forward. Future work includes enclosure refinements, calibrated sensing, expanded environmental inputs, exploring more synthesis capabilities through programming structures, and longer duration reliability testing. The next steps for the room project would be to split it into an educational open hardware version and an integrated production version. The educational version would keep the form factor that it currently has, keeping it modular and open for experimentation. The integrated production model would have a custom PCB, power distribution, a reduced enclosure size, and panel-mounted controls. These are references, sources supporting the software architecture, hardware selection, calculations, design method, validation, and future work spanning Arduino, processing documentation, sensor data sheets, and the engineering text we use for the calculations and design methodology. Thank you very much. We appreciate your time.
This demonstration presents the completed room's procedural generative synthesizer operating as a fully integrated environmental audio-visual system. At startup, I am opening the software environments and establishing communication between the hardware, visualization, and sound processing layers. The Arduino Mega functions as the embedded control layer. It reads the ultrasonic sensor, environmental sensor, potentiometer, and push-button controls. That information is transmitted through serial communication to processing, which provides the graphical interface and translates the data into open sound control messages. Super Collider receives those messages and generates the procedural audio output. The complete signal path is therefore sensors and user inputs, Arduino Mega, serial data, processing, OSC communication, Super Collider, and finally stereo audio output. Once all three environments are communicating, the system begins responding continuously to both the room and the operator. The first function being demonstrated is the core environmental interaction. The ultrasonic sensor is mounted to a servo and continuously sweeps across the surrounding space. As an object enters or leaves the sensor's detection area, the measured distance changes. That distance is not simply displayed as a number. It is mapped into the synthesis engine, allowing the physical arrangement of the room to modify the sound in real time. As I move the object closer to and farther from the sensor, listen to how the audio responds. I am now cycling through the available oscillator waveforms. The system includes sine, sawtooth, square, and triangle waveforms. Each waveform contains a different harmonic structure, so changing the waveform significantly changes the character of the same environmental modulation. The waveform change is confirmed locally on the LCD, visually in the processing interface, and audibly through Super Collider. The next control cycles through the adjustable parameter modes. A shared potentiometer is used to modify whichever parameter is currently selected. This reduces the number of physical controls while still providing access to several synthesis functions. The available modes include pitch, filter cutoff, filter resonance, LFO rate, LFO depth, and arpeggiator speed. Filter cutoff controls how much of the upper frequency content is allowed through the sound engine. Resonance emphasizes frequencies near the filter cutoff point, creating a more pronounced or sharper tonal character. The low-frequency oscillator, or LFO, creates repeating modulation. LFO rate determines how quickly that modulation cycles, while LFO depth determines how strongly it affects the sound. The final mode controls arpeggiator speed, which becomes especially noticeable after the arpeggiator is activated. As I rotate the potentiometer in each mode, the processing meters provide visual feedback, while the audio gives immediate confirmation of the parameter change. The freeze function temporarily stops the evolving modulation and holds the current state. This gives the operator a way to capture a particular moment produced by the interaction between the sensor, the room, and the synthesis engine. When freeze is released, the system returns to active real-time modulation. Lastly, we show the randomization function. Each press generates a new combination of pitch, filter cutoff, resonance, LFO rate, LFO depth, arpeggiator speed, and waveform selection. The randomization function also activates the arpeggiator, producing an immediately audible procedural variation. I cycle through several randomized states to show the range of behaviors the system can produce without manually adjusting every individual value. Although the settings change automatically, the system remains connected to its environmental input. The resulting sound is therefore created through a combination of procedural generation, sensor information, and user interaction. This demonstration confirms the primary operating goals of the Rooms project. The ultrasonic sensor successfully influences the audio output, all 6 push-button functions respond correctly. Parameter adjustments are reflected visually and audibly, and the Arduino, processing, and Super Collider environments remain synchronized throughout operation. More broadly, Rooms demonstrates how embedded sensing can transform normally unseen environmental conditions into an interactive audiovisual experience. It functions not only as a synthesizer, but as a platform for exploring the relationship between physical space, real-time data, visualization, and procedural sound.